Okay, so now that we've got a better idea of what the nucleus looks like, let's focus on those electrons, because actually chemistry involves the electrons. We don't mind so much what's going on in the nucleus, aside from a little bit of nuclear chem we'll touch on with radioactivity. The bulk of our concern are those electrons outside the nucleus. So in this subchapter, we're going to look at electron arrangement in atoms, and we're going to start to understand better why things like those alkali metals, that first group, the vertical column underneath hydrogen, and why that second to last column there, the halogens, group 17 or 7A, why they're so reactive, and why we have things like the noble gases that are pretty unreactive. It all has to do with electron arrangement in atoms, which is the focus for this subchapter. So to summarize what we've talked about so far in Chapter 3, atoms have a very small, very dense nucleus that has the neutrons and the protons, and again, there are smaller subatomic particles, but that's where we stop with our level in this course. And those protons and neutrons are massive. The neutrons are neutral, the protons are positively charged, but the overwhelming majority of mass in the atom is focused in that small, dense nucleus. The volume of the atom is defined by those small, light, negatively charged electrons that are moving very quickly to define that volume of the atom. And so it's the electrons that determine the physical and chemical properties, more so the chemical properties, because physical properties do differ between isotopes. When you have a heavier isotope, it does behave different physically speaking than a lighter isotope. So there are some physical properties that do depend largely on the nucleus, because the isotopes differ based on the number of neutrons, but the chemical properties, aside from nuclear chemistry, which we barely touch on in this course, the overwhelming majority of the chemical properties we investigate have to deal with the electrons. Alright, so the items we're going to discuss here are the result of over 100 years worth of work on trying to figure out the atom. So we're going to drop some terms that may not make a whole lot of sense. A lot of it involves quantum mechanics, which makes sense to very few people. So let's just take it at face value, and again, if you're having trouble or struggling with any of these concepts, get in touch with me. Some of the concepts are beyond us and you don't have to worry about. We just touch on some of the quantum mechanical stuff, but other things like energy levels and other items we'll discuss are pretty central to our understanding of chemistry. So electrons surround the nucleus in specific energy levels, and each energy level has what's known as a principal quantum number. So if we're looking at the periods on our periodic table, those correspond with principal quantum numbers. So hydrogen and helium, they have electrons occupying that first principal quantum number in the ground state. So they're the closest to the nucleus, the lowest in energy. They're labeled n equals 1. The second lowest would be n equals 2, and that's where we start with things like lithium and so on and so forth. And then we move into 3 with sodium. And every time we move down a horizontal row in the table, we're increasing our quantum number. We're increasing the distance from the nucleus, increasing the energy of those outermost electrons. Okay, so as we just said, as we move higher and higher in principal energy levels, the electrons get further and further from the nucleus. And so we have our analogy here on the slide with the books. The books on the lowest shelf, they don't have a whole lot of energy, potential energy, stored there. If they fall a relatively small distance. They have very little potential energy to convert into kinetic energy as they fall. As we move up, the shelves get higher. They also get closer together, which ordinarily isn't the case for most bookshelves I've seen, but for this analogy and for the atom itself, that's true. The energy levels get closer together, and it's easier for electrons to move between energy levels as you go up. It doesn't take as much energy to promote an electron, for instance. There's a big gap between n equals 1 and n equals 2, but those energy level gaps get smaller and smaller. Other features of increasing the value of n, that principal quantum number, it can hold more electrons. So we don't show this in the bookcase, but I guess it should have widened as it goes up as well, because that's true. At the bottom, at least, what Timberlake's graphic here does show is we've got 2 books in the n equals 1, and then we go up to what ultimately should be 8 books in n equals 2, and so on and so forth. So the electrons get higher in energy, they're further from the nucleus as n goes up, and you also can have more electrons in those higher level of n values. Alright, so the main reason why we can accommodate more books on our higher shelves, or if we want to be more explicit, more electrons in higher principal energy levels, is that we have sublevels that exist. And so the sublevels contain electrons that are what we call of the same energy, or the term we actually use is degenerate. So that means of the same energy. It's not the same everyday use of that term, but in chemistry and physics, the term degenerate means all of the same energy. So those sublevels tend to have electrons that are what we call degenerate. They're identified by the letters S, P, D, F. We do get some interesting things happening where some of the sublevels get split and they're not of the same energy anymore, but that's beyond the scope of this course. If you go on in chemistry, you'll learn all about that. So the number of sublevels within a given energy level is equal to the value of the principal quantum number. So when n equals 1, we're in the first period of the periodic table, you see just 2 elements, hydrogen and helium, because there's just one type of orbital, an s-type orbital. When we go to n equals 2, now we have an s and a p, because principal energy level 2 has 2 sublevels, the s sublevel and the p sublevel. The s can accommodate 2 electrons, and therefore we have 2 elements, just like in period 1 we had 2. In period 2 we have 2, and then we also have the p's, which can accommodate a total of 6 electrons, so we have another 6 elements and a total of 8 electrons, and therefore 8 ground state electron configurations, and in the periodic table 8 elements in period 2. And then as we go up it increases, but things get a little tricky once we go into n equals 3. And here we have a nice graphic of that, where n equals 1, we have 1 sublevel, the s-type sublevel, and then n equals 2, we have 2 sublevels, s and p. N equals 3, we now have 3 sublevels, s, p, and d. And then n equals 4, we have 4 sublevels, s, p, d, and f. And notice that there's 1 s orbital, 3 p orbitals, or sublevels, I guess we're still calling them here, 5 d sublevels, and then 7 f sublevels. So every time we get a new sublevel, we get 2 more orbitals, or 2 more boxes here in the picture than we had in the previous one. So it goes 1 box for s, 3 boxes for p, 5 for d, 7 for f. We're counting up by 2s there, starting at the number 1 for our s sublevel. So if we're thinking about a given principal energy level, within any of those given energy levels, the s sublevel is always going to be the lowest energy. There's always some probability of finding s electrons at the nucleus, and so therefore they tend to have a lower energy than things like p sublevels, which is the next sublevel in energy after s, and those are slightly higher in energy. They have a node at the nucleus. There's no chance for those electrons to be at the nucleus, so they're higher in energy. D sublevel is even higher in energy than P. Again, just like that bookcase, the shelves narrow, that's the same sort of idea is going on here. So the D sublevel is a little higher than P, and then the F sublevel is a little higher than the D. Alright, so each of those sublevels consists of 1 or more orbitals, and an orbital, if you think back to the old Bohr model of the atom, where you had sort of like electrons being planets around the nucleus being the sun. That's not quite true, but that gave us a good basic understanding of how electrons behave in atoms, and that's when back then we called them orbits. Now we understand it's a lot more complicated than that, and so we use the term orbital. And these are regions where there is the highest probability of finding an electron. We deal in probabilities and waves now with quantum mechanics, instead of that idea of discrete planet type circling around the nucleus. So each orbital has its own unique three-dimensional shape, and each orbital can hold up to 2 electrons, one that we call spin up and one that we call spin down. So that's why in the S sublevel we can have 2 electrons, and therefore when we have just the S sublevel and principal energy level 1 on the periodic table, what corresponds with period 1, hydrogen and helium, we have those 2 elements because we have up to 2 electrons that can be housed in that S sublevel, that S orbital, to be more exact. Okay, so for the S orbital, fortunately the shape goes nicely, although the S didn't originally stand for spherical, it stood for sharp from spectroscopy lines, but S orbitals do have a spherical shape that's centered around the atom's nucleus. S orbitals get larger as principal quantum number n gets larger, so every principal quantum number has an S orbital, including n equals 1, which only has the S orbital. We see over in the bottom right of the screen an image of an S-type orbital, a spherical orbital. And then over to the left, we have the 1s, 2s, 3s orbitals. We see these nodes, these regions where electron density can exist in the n equals 2 and higher S orbitals, and again, that is a bit strange because the electrons exist on either side of the node, but they can't exist in the node, so that's sort of electron teleportation, which happens all the time, although of course humans can't teleport, the electrons can and do. And each of the S orbitals can hold up to 2 electrons that spin in opposite directions. And that's what gives rise to this spherical type orbital. The electrons are moving very fast. The highest probability of finding them is in this spherical shape. And it gets less and less likely to find them as you get further and further from the nucleus. So that's why the density there on that far right image gets lighter blue as we move further from the nucleus. If we now consider the next orbital type, the p orbitals, there are 3 p orbitals, and they start in principal energy level 2, and then every level 2 and beyond has those p orbitals. They're a 2-shaped lobe, like sort of tying a balloon in the middle, and you have density on either end. And each of those p orbitals can hold 2 electrons, and they're centered along the x, y, and z axis, so that you can have, again, all 3 of those p orbitals come together to give something roughly spherical when you consider the s orbital and the p's, and then as we think about d's and f's, which I won't show images of because they get a little complicated, but at least the s's and the p's are simple enough shapes that we can wrap our mind around them. They, just like the s orbitals, the p's increase in size. I don't show the different p orbitals for 2p or 3p, but they all have that same, I would sometimes call it a dumbbell or a lobe shape, and each of them can hold 2 electrons with the 3p orbitals, the px, py, pz. That's a total of 6 electrons, and that's why groups 3a or 13 through 8a or 18, those are filling or have filled the p sublevel, and that's why there's 6 elements in that region of the periodic table. Just like there's 2 over in the far left. Groups 1 or 1a and 2 and 2a would be typically filling s orbitals or have just filled the s orbital. The exception is helium, which we stick way over in row 8a or 18, and that's just because with just the one s orbital there, it didn't seem right to have hydrogen and helium right next to it, especially since helium is a noble gas. We placed it over in the table with the rest of the noble gases. Okay, so we already talked about this, that we're sort of counting by 2s starting at 1 here, because each sublevel has a specific number of orbitals. The s sublevel has just the 1 spherical orbital. The p sublevel, each p sublevel, just like each s sublevel, has 3 p orbitals, and then each d sublevel has 5 d orbitals. Each f sublevel contains 7 f orbitals, and if we keep making elements, we'll eventually have to consider the G sublevel, but so far the S, P, D, and F are the only sublevels that have electrons occupying those sublevels in the ground state for the 118 elements we have today. Looking at table 3.9 from the text, we see the number of sublevels and total electron counts for each energy level, principal energy level n in the table. So n equals 1, the first period, we have a total of one s orbital, which can have a spin up and a spin down electron for a total of 2 electrons, and that's why we see 2 elements, hydrogen and helium. For n equals 2, we have the 1s orbital in the 2 energy level, and we also have the 3 2p orbitals, 2px, 2py, 2pz, so we can hold a total of 8 electrons. We have the 2 electrons in the 2s and the 6 electrons in the 2p. Of course, we also have 2 electrons in the 1s orbital, but we don't think about those. They're not what we consider in terms of chemistry, because chemistry happens in the outermost energy level. So there's a total of 8 elements because of 8 electrons, so that's where we get lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon is period 2. Those 8 elements coming from that idea of being able to fill 8 electrons in the 3 2p orbitals and the 1 2s orbital. Okay. When we get to D, we should be able to have a total of 18 electrons because we have those d orbital 5d orbitals, which gives a maximum of 10 electrons, but we don't start to occupy the 3d until after the 4s. So that's why you see that middle region there, the transition elements. The first time we see them is in period 4 of the table, even though those are the 3d orbitals that we're filling. The 4s is slightly lower in energy, so we actually fill the 4s first and then go back to fill the 3ds. The same sort of thing happens when we get down at the bottom with the F sublevels. Those 2 rows down at the bottom, the lanthanides and actinides, those are actually, the lanthanides are filling the 4F, but they don't start to do that until after they filled the 6S. So the D sublevel actually starts to get filled 1 energy level higher than you'd expect it. We start to fill it in principal energy level 4, even though it's the 3Ds. And the Fs get filled 2 energy levels higher than you'd expect. So we're finally filling the 4F after the 6S. We're finally filling the 5F after the 7S orbital. So things aren't quite as user-friendly there, as logical as we might hope, but at least knowing those little tidbits, and fortunately for us, the elements we tend to deal with are the S's and the P's that do follow the rules. We should be able to get our mind around these things, at least for the level you're expected here in Chem 141. Alright, so before we leave this kind of convoluted topic, let's see how we're doing. So we'll pause now for a learning check, and this will be your chance to see if it's making sense. I know it's a lot, and it's very different, and suddenly seems to come out of nowhere after we were talking about very simple ideas like neutrons and protons and electrons, and now suddenly these electrons are doing all of these interesting things. Let's just see how you're getting the core concepts here. So this learning check: indicate the number and type of orbitals in each of the following. 1, a 4s sublevel, 2, the 3d sublevel, and 3, principal energy level, n equals 3. So go ahead and list the number and types of orbitals that you would find in each of those regions. Okay, so hopefully you arrived at 1 orbital in the 4s sublevel, because that's all we have is the 4s orbital, and it could hold up to 2 electrons, but there's just the 1 4s orbital. For number 2, the 3d sublevel, we have 5 orbitals. There's 5 d orbital types, right? There's 1s, there's 3 p's, there's 5 d's, and there's 7 f's for any given sublevel. So that it doesn't matter if we ask about the 3d or the 4d or the 5d sublevel. Any of those sublevels will have 5 d orbitals present. Finally, if we consider every type of orbital present in n equals 3, well, whatever n equals, that's the number of different orbital types we have. So since n equals 3, we have s, p, and d orbitals, and we have 1 s orbital, the 3s, there's just 1 of it, and it can have 2 electrons spin up or spin down. There's 3 of the 3p orbitals, 3px, 3py, 3pz, and each can hold 2 electrons. And then just like in number 2 here, there's 5 3d orbitals. So it's a total of 9 orbitals a total of 18 electrons that can be accommodated in all of n equals 3, but recall those 3 d orbitals don't get filled until after the 4s. Okay, why don't we try another learning check? Hopefully this wasn't too bad, but let's do one more to make sure you're really getting these concepts. Okay, so for this final learning check before leaving this subtopic, we want to know the number of 1 electrons that can occupy a p orbital, 2 p orbitals in the 2p sublevel, 3 the number of d orbitals in the n equals 4 energy level, and 4 the number of electrons that can occupy the 4f sublevel. So go ahead, make your selections there, pause the video if you must, and we'll check and see how you did when you're ready. Okay, so the number of electrons that can occupy a p orbital is, and be careful, this is something that we chemists love to test. We're not so much testing your concept mastery as your ability to read carefully. So there are 3 p orbitals, and the p sublevel can hold a total of 6 electrons, but any one p orbital, any one of any orbital type, can only hold 2 electrons. So a spin up and a spin down. It doesn't matter if I ask you about an s, a p, a d, or an f orbital. If I'm asking how many can occupy an orbital, no matter what orbital type it is, only 2 electrons can occupy an orbital. Number 2, the number of p orbitals in the 2p sublevel is 3, right? For any sublevel that contains p electrons, so n equals 2 or larger, we've always got the px, py, pz for any energy level n equals 2 on up. Number 3, the number of d orbitals in the n equals 4 energy level is 5, and that's the same deal. We start to get the d's in n equals 3, and then we start to fill them after the 4s on the table, but the number of d orbitals in any energy level 3 or above is going to be 5. And then finally, the number of electrons that can occupy the 4f sublevel is C14, right? There's 7 f orbitals in any of the f sublevels, 4 on up for principal energy level, and therefore, since there's 7 orbitals and each orbital can accommodate a spin up or a spin down electron, or more correctly, a spin up and a spin down, we can have a total of 14 electrons occupying that 4f sublevel. So I think probably most everybody out there needs to do a little more practice with this. There are some homework set questions on it, but the end of chapter questions, I would strongly advise that you look at several of those as well, and please get in touch. Let me know where you're having trouble, if you're struggling, and how I might be of help.